Lesson 1.2, functions and function notation. So we're familiar already with the function machine here. We know that we have our input values that go in. They're represented by x, which is all the values in the domain. And then some kind of mathematical operation happens to them, and out pops a y value, or our output. And all of the y values that come out constitute the range, okay? And what this function machine creates is a set of ordered pairs. An ordered pair is simply an x and a y that belong together. An x goes in, a y comes out. Okay, you put in a different x and another y comes out. You put in a different x and another y comes out. Okay, and this might be a finite set or it might be an infinite set depending on the function itself. Now what we want to talk about today is something called function notation, which is basically right here, f of x. Okay, so here we go with a little note off to the right, function notation. When we get a function and we write it in the form f of x equals, and then whatever that function actually is, the equation that belongs to it, what we're saying is that there is a function called f with an independent variable x. So the value of the function depends on what we put in for x. And that's what we're going to be doing in example 1 today, is just putting in different values for x when we have a given function and seeing what value we get for that value of x. Okay? So what is that notation? Well, first let's read this. This means literally the function of, the function f with respect to x. It simply means that the value of the function changes when x changes, x being the independent variable, the value of the function being the dependent variable. Another way that we say this is simply f of x. Okay, well, we can also find not just the function in general, f of x, but we could also find f of 3 equals. Okay, well, what does that mean? That means you've taken the value 3, you've put it in the function everywhere you see an x, and you get a value of the function when x is 3. Okay, so what does this mean? This is read as f at 3, or you might hear it f of 3. I'll quite often actually say the value of the function at x equals 3. Okay, there's some function notation, there's some terminology that we use. Get familiar with it, get used to it, and here we go. So in example 1, we're just asked to plug in a value for x in the function that's given and see what comes out. So we have basically our function machine right here. We're going to put in -2 for x. So everywhere we see an x, we're going to put in -2. Then we're just going to do basic algebra and see what we get. So the function given, f of x equals 2x minus 4. And we're going to see what we get when we sub in -2 for x. Well, that means I copy down what I have. Remember, multiplication is the default operation of algebra, so this 2x means 2 times x. So it's easiest if I put my value in brackets, and that way, especially because it has a negative sign, I can see that the negative sticks with the number 2. Over here, -4. I am using my algebra tools, for instance, BEDMAS, to determine which operation to perform first. In this case, multiplication comes before addition and subtraction. So I'm going to go 2 times -2, which is -4, -4. -4 minus 4 is -8. So the value of the function when x equals 2, -2, sorry, is -8. The ordered pair that would give us is -2, -8. That would look like this. We don't need to do it, but to give us a heads up, we just produced that ordered pair. And we could plot that graph. And if we did plot all the points, infinite number of points for this function, because there's no restriction on the domain, we would get a straight line with a slope of 2 passing through y-intercept of -4. Okay, well, that's one of them. Let's go for f of 5 in this case. Again, 2 times 5 minus 4. 2 times 5 is 10, minus 4, 6. Carrying on a little more quickly here. Notice how in our examples they give us a negative to try, they give us a larger positive number to try, then they give us a fraction to try. Okay, it's good to try all those things. And in following examples, they add another element or they change it up slightly to make it a little more difficult, just so that you can see all the possibilities. Anyway, here we go. Here we have x is 1/2, so I sub in 1/2. Notice also I didn't convert this to 0.5. Okay, get used to working with fractions. They're much more helpful than decimals in the long run. And actually, if you learn how to use them properly, they're actually easier to use than decimals in a lot of ways. Right now I can see this is 2/2, which is 1, minus 4, -3. Okay, and the ordered pairs that we created, I'm not going to do this every time, but we created the ordered pair 5, 6, and we created the ordered pair 1/2, -3. And you could graph those things. Let's head over to B. I'm not going to do all of them, but let's do it for -2. Everywhere I see an x, I'm going to put in -2. And again, I'm using my brackets so that it helps me keep things organized. A couple of reasons why. Here, I see I have a -2 squared. Just a quick note off to the side. -2 squared is -2 times -2. It's +4. But watch this. This also says -2 squared. But in this case, I have to do the square part before I apply the negative. So in this case, I have 2 squared, which is 4, and I have negative that, which is -4. So very important to be careful with your signs, with your operations, with your brackets, okay? All right, well, I'm going to break this down into steps, but I'm going to do a couple at once. So I'm doing my brackets and my exponent first here. So I have -2 squared, which is 4, times 3, which is 12. And then look, I have -2, or minus -2. Well, 2 negatives makes a positive. Or I could visualize this as a -1 times -2. Well, that's +2. And I have a +7 out there. That gives us 12 plus 9, which is 21. Okay? Let's see what happens when I put the fraction in there. I'm going to skip over f of 5 and go to f of 1/2. If you need the extra support, you can do that one on your own and check your textbook. But all I'm going to do is everywhere I see an x, I'm going to put in 1/2. Notice I didn't bracket it here because I don't need to. I have a negative sign and this value doesn't have a sign. I could do it, but it means the same thing, -1/2. Now here I need to make sure that I multiply 1/2 by 1/2 first. I need to square it. Well, 1/2 times 1/2 is top times top, 1 times 1, bottom times bottom, 2 times 2. Or another way to think about it is square the top and square the bottom. So that's 1/4 times 3, 3/4. Now watch what I do here. Because I know that I'm going to be adding and subtracting fractions, right away in this next step, I'm not just going to bring down -1/2. I'm actually going to convert -1/2 into a fraction over 4. Well, what fraction with a denominator of 4 has the exact same value of 1/2? Well, it's 2/4. I'm going to do the same thing with the value of 7. How can I represent 7 as a fraction over 4? Well, I'd need 4 times 7. 28/4 is the same as 7. And now I have all of my fractions over 4, which means I can actually add them. I'm dealing now with fourths. I have 3/4. I'm going to take away 2/4. I'm going to add 28/4. What does that get me? 29/4. 29 is not divisible by 4, so this is reduced. This is my final answer. I'm not going to convert this into a decimal, okay? I'm going to leave it as a fraction. If I wanted to, I could convert it to a mixed fraction, in which case I would have 7 1/4, but I don't need to. This is sufficient. All right. All right, heading down to example 1c, we're given the function f of x equals 11. Well, this is pretty easy. It always equals 11. It's not dependent on the value of x. There's no x over here. So if I put in -2 over here, there's nowhere to put it on the right side. It's still just 11. This is what we call a constant function. Constant function. A couple ways to think about that. It's constant because it never changes. It doesn't matter if x is -2 or 5 or half, makes no difference. This function, the value of it, is always going to be 11. Another way to help us remember it is what's true about an equation when it has a few terms, but there's a term in it that has no variable. What do we call that term? For instance, f of x equals 2x squared plus 4x minus 7. This term has a variable, this term has a variable, this term doesn't. It's called the constant. It's the one value in the function that will never change no matter what x is. So this is a constant function, never changes. It's actually just a straight line at y equals 11. Because no matter what x is, the value of the function is 11. Okay, constant function, straight line, horizontal line. Good. So, I mean, let's do a couple quickly, but the value of the function at -2, that's 11. The value of the function at 5, well, that's 11. And the value of the function at 1/2, well, you guessed it, 11. Let's carry on. This one's a little bit more challenging. It's called a rational function because it has the variable in the denominator as well. We're not going to worry too much about that. We're just going to go ahead and see what happens if we plug in a value of x equals -2. So in the numerator, I've got 2 times -2. In the denominator, I've got -2 squared minus 3. Now we're going to do this step by step, carefully, right? First thing I like to do is draw my equal sign, give myself some space, so it's nice and neat and organized. I've got room for a numerator, room for a denominator, and here we go. 2 times -2 in the numerator, -4. Now in the denominator, I'm remembering I do my exponent first, and it looks like the -2 is in the bracket being squared, so that's -2 times -2, which is +4. And +4 take away 3, that's 1. -4 over 1, well, -4 wholes. That's just -4. I'm going to go ahead and skip f of 5 again and just go to f of 1/2. I think that's enough for us to practice. So copy down my function, and anywhere I see an x, I'm going to put in half instead. We're going to really draw on our algebra skills that we've developed over the years. Again, equal sign, division line, 2 times 1/2, that's 1, right? 2 halves, or half of 2, it's 1. 1/2 squared, that's 1 squared over 2 squared, that's 1/4. I'm going to do this one in 2 steps. I've got 1/4 minus, and now remember, because I have addition and subtraction, I don't want 3 as is, I want 3 expressed as a fraction over 4. Well, what fraction over 4 is the same as 3? It's going to be 12/4. I need 12/4 in order to have 3 wholes. What happens here? I've got 1 over 1 minus 12. That's -11/4. Now, there are a couple ways to think about this. I'm going to do them off to the side, and if you need this help, you can use it. Otherwise, just stay posted for the little trick that I have for you. But basically what this is 1 divided by -11/4. Okay? Well, division is the same as multiplication by its reciprocal. And it doesn't matter where I put the negative sign, as long as there's only one piece that's negative, I'm going to end up with a negative answer. And now what we have is top times top, bottom times bottom. That's multiplying fractions, which is a lot easier than dividing fractions. So I've got in the top -4, the bottom 11. Okay, so this reduces to -4 over 11, which points out another really easy trick that you have. If you ever have one value in the numerator, okay, it gets a little trickier when there's a fraction here and a fraction there. We could explain that when it comes up. But basically, look at what happened. All we needed to do was, if we're flipping this guy and multiplying it, then really all we ended up doing is taking this 4 and multiplying it by the 1, chucking it in the numerator. So it ends up being, instead of 1 over 11 over 4, we've got 4 times 1 over -11, which reduces to -4 over 11. Okay, there's a little trick for you. That's example 1. You can now find the value of any function as long as you're really careful and you're applying your algebra skills and the order of operations, brackets, then exponents, then division and multiplication in order from left to right, then addition and subtraction in order from left to right. We'll also come across pictures, which are called mapping diagrams. And all it is a visual representation, a graphical representation that relates the values from the domain, the input values, to the values in the range, the output y values, using arrows in a real visual way. So here we go. It just looks like this. They give you some nice ovals usually. And let's say the domain consists of 1, 2, 3, 4, and 5. Domain. And let's say the range. The range consists of 1, 4, 9, 16, 25. Well, hopefully you can see what kind of function we're dealing with here. In a mapping diagram, the values from the domain map directly to the values from the range, and they're indicated like this. Pretty simple. There's a mapping diagram. So if you're asked to develop a mapping diagram for the function, in this case we know it's f of x equals x squared, for the values of x between 1 and 5, this is what it would look like. Okay? Again, it is a graphical representation. It is a graphical representation that relates the values from the domain to the values in the range using arrows. Wow, that's really deep. Okay. Let's carry on then. Example 2. And leave that up there. I think we have enough space. Example 2. Interpreting mapping diagrams. We're going to use the mapping diagram to first write a set of ordered pairs for the relation, and then state if the relation is a function, okay? So the ordered pairs that you have a drawing in your notebook, so I'm not going to draw mine, but we're going to just write the answer. First, the set of ordered pairs. Remember, set notation opens with a squiggly bracket, and then within there, we're going to have all of our ordered pairs. So I see that 1 maps to -5. Then we have 2. It maps to -1. 3 maps to -5. Okay. 4 maps to 0. 5 also maps to 0. That's okay though. 6 maps to 5. And 7 maps to 8. And I'm going to close it, the set, with another squiggly bracket. And let's take a look at this. Are there any values of the domain that go to two different numbers? Or is there a unique value in the range for every value in the domain? Well, I'm looking and I don't see any arrows going from a number in the domain to two different places, and I don't see in my ordered pairs any repeated values of x. Okay, so since every value in the domain maps to exactly one value in the range, this relation is a function. Ready? Every value of x maps to exactly one value of y. I'm just subbing in the word x for domain and the word y for range. Every value of x maps to exactly one value of y. ... function. All right. That was set A. Let's take a look at set B. You go ahead and develop the set of ordered pairs. Pause it here and check back, see how you did. Okay, I have my set of ordered pairs, and I'm going to analyze this. I can see it from the drawing, from the mapping diagram, but I can also see it from my set of ordered pairs, that the value for x equals 2 maps to 1, and then here it maps to 2. Well, that's no good. We have the same case with 14. 14 maps to 4, and it maps to 6. 14 should always map to the same value in the range. It doesn't. 2, in order for this to be a function, needs to map to the exact same value every time I put it into my function machine. It doesn't. Okay? Since x equals 2 and x equals 14 map to more than one value in the range, relation, not a function. So if we're given a function as a mapping diagram, we're given a mapping diagram of a particular relation, then we can make a list of ordered pairs and determine if it is a function or not and learn some things about it, and also vice versa. If you're given a set of ordered pairs, you can create a mapping diagram which can help you determine some things about that function. That's not always super helpful because more often than not, we're given the function in terms of an equation using function notation and mapping function notation, which we talked about a little bit earlier. So now what we're going to do is go from kind of function, and we're going to write what's called mapping notation. So this is a mapping diagram, but we also have something called mapping notation, which is pretty simple, really. You just take the function that they've given you, and you write it in the form that says it maps to. So I'm going to just write what the mapping notation is for this one, and then I'm going to write it in words, and then we'll work down our way. Notice what they've done again with examples. They give you a quadratic, they give you a linear, then they give you this guy, which is actually dealing with gravity. So anything falling falls at a rate of acceleration of negative 4.9 meters per second. And then they have this one, which is a maximizing profit type format. We're not going to do any work with them, but it's good to be familiar. This is kind of like, you know, Susie, who owns the snowboard shop, and she is going to drop her price by a certain number of increments. And if she does that, her rentals are going to go up by a certain number per weekend. And what does the price need to be for her to make the most amount of money? Anyway, total side note. But here we go. Function mapping notation. This is function notation right here. Okay, get familiar. And mapping notation is this. F is a function that maps x to 3x squared minus 2x plus 1. Wait a minute. What did he say? Okay, here's how you read it. F is a function that maps x to the expression given, 3x squared minus 2x plus 1. All right, let's do that again. What's going on here? Well, g is a function that maps x to 3x plus 4. I'm going to write it again. G is a function that maps x to 3x plus 4. You go ahead and try the next one. Check back to see how you did. All right. H is a function that maps x to negative 4.9 t squared minus 4. And P is a function that maps x to 500 minus 2x times 300 plus x. Now this is mapping notation. You can now go from mapping notation and develop your function, or you can take your function and write it in mapping notation. All right, last example, let's solve a word problem. We have Ronaldo. He's scuba diving in a deep lake. Here's his top of the water here. And the temperature at the top of the water is 22 degrees Celsius on a warm summer's day. As he dives, he finds that the temperature decreases by 1.5 degrees Celsius for every 8 meters. Okay, so every 8 meters, that means it's kind of like, okay, here's 8, here's 16, here's 24. He's going deeper and deeper. But, I mean, it's not layered. Every meter that he dives, it's going to be a little bit colder and a little bit colder and a little bit colder, but it's only going to be a fraction of that 1.5 degree change. Is this realistic? Well, maybe. I mean, water actually layers in temperatures, or it might even get colder faster as you go lower. But for the sake of our example, it's linear, and it's going to be a consistent rate of change of temperature as Ronaldo does his dive. So what we're going to do is we're going to model the water temperature at any depth with the information that we have using function notation, okay? So we're going to make a model using function notation. Well, the first thing that we need to do then, as always, is introduce some variables. There's a couple variables here, two, a dependent variable and an independent variable. The dependent variable is probably easier to identify. It's temperature, but we're going to do our independent variable. Well, our independent variable is just Ronaldo diving. It's the depth of the dive. So we're going to let D be depth in meters that Ronaldo is below the surface of the lake. And we're going to let T be temperature measured in degrees Celsius, okay, at a particular depth. What does that mean? That means we're going to get the temperature with respect to the depth, okay? So we're developing a function here. That means we're going to have T with respect to D. That means the temperature is going to change as his depth changes. Well, what do we know? We know that when depth is 0, the temperature of the water is 22 degrees. So we're starting 22 degrees. Then what's happening? Well, the temperature is dropping. And the information that we have says it's dropping 1.5 degrees Celsius for every 8-meter increment. But what if he only goes 1 meter or 2 meters or 3 meters? Then it's only going to reduce by a fraction of that 1.5. So what we actually have here is we're going to take the actual depth and divide it by 8. So if he dives 8 meters deep, we'll have one full increment, 8 over 8 times 1.5, one full increment. But if he only dives 2 meters deep, we'll have 2 over 8, a quarter of that 1.5 increment. He'd be somewhere up here, okay? So this is our function. It's in function notation. T with respect to D equals our original temperature, and then the effect of diving deeper is represented in this portion of the function, okay? The temperature decreases by 1.5 degrees Celsius every 8 meters. What does B say? Use this function to determine the water temperature at a depth of 40 meters. Well, a depth of 40 meters. T depends on D. So all I need to do is put 40 in everywhere I see D. So nice of them to give us a multiple of 8 to deal with. Let's reduce this step by step using BEDMAS. I need to deal with what's inside the brackets first. I need to reduce this. Okay, so I'm going to be left with 1.5 times 40 over 8 is 5. You could put this whole thing in your calculator if you knew how to do it right, but here we go. We're going to continue on. 1.5 times 5 is 7.5. So we've got 22 minus 7.5, which is 14.5. And a concluding statement. Therefore, the temp at a depth of 40 meters is 14.5 degrees Celsius. All right. What does C say? C says, at the very bottom of the lake, the temperature is 5.5 degrees Celsius. How deep is the lake? So this time, we are not given the depth. Instead, we're asked to find the value of T of D. So we don't know the value. We don't know the temperature at that depth. Sorry, we do know the temperature at that depth. We don't know the actual depth. So I'm just going to copy down my original equation here. T of D equals 22 minus 1.5 times D over 8. And this time we do know this whole chunk. We know this is going to be 5.5, but we don't know how deep we are. Okay, that's going to be the depth of the lake because it's the bottom of the lake. So what do we need to do? Well, we simply need to use our algebra skills to solve this thing, to figure this out. I want to get D by itself. It's going to take a few steps to do that, okay? So please pay attention on how we can undo the algebra operations here in order to finally get D by itself, okay? One way to do it is to write yourself BEDMAS. And this time, because we're solving for a variable that's not isolated yet, we want to isolate that variable, we're actually going to use BEDMAS in reverse. What does that mean? Well, the things that D is most stuck to are going to happen last. And the things that are more peripheral are going to happen first. Okay? So I'm trying to get D by itself. I want to strip, the divided by 8 away from D. I want to strip the 1.5 away from D, and I want to strip the 22 away from D so that D is the only thing left over here. Well, it's really stuck with divided by 8. That's in brackets. So that's actually the last thing that I'm going to do. Then I look at this, and default operation of algebra is multiplication. So D over 8 is being multiplied by negative 1.5 or being multiplied by 1.5. Well, that's here. But then that whole chunk has 22 being added to it. So that's actually what I'm going to strip away first. Another way to see that is just visually. These guys are a really tight unit, and this guy's just hanging on out there. So I'm going to get rid of him first. I'm going to show you each step carefully, just because it's the first time we're really going through something like this in this course. This should be review, But here we go. If I see a positive 22, and I don't want it here, I want to get rid of it. Well, how do I get rid of positive 22? I simply subtract 22. And if I subtract something from one side, if I do something from one side of the equation, I have to do the same thing to the other side. Otherwise, I'm creating a lie. It wouldn't be equal anymore, or at least this statement wouldn't be equal to the next statement. So what does that look like? 5.5 minus 22 ends up being negative 16.5. Negative 16.5 equals, and on this side I don't have that anymore, but I do have negative 1.5 times d over 8. Now at this point I'm looking at this and saying, well, negative numbers, I don't really want to deal with negative numbers. So what are we going to do? Well, let's just do our next step. I've got d over 8 multiplied by negative 1.5. It's being multiplied by negative 1.5. Well, what do I need to do to undo that? I need to divide this whole side by negative 1.5. If I do something to the right, I must do it to the left. Okay, so over here on the right, it's pretty straightforward. Those guys cancel out, and I'm just left with d over 8. And on the left-hand side, 16.5 divided by 1.5. I could do that now, or I could leave it until later. For this example, I'm going to do it right away. 16.5 divided by 1.5 is 11. And a negative over a negative, two negative factors, that creates a positive. Okay, so now we have 11 equals d over 8. I've done my addition opportunity and my multiplication division opportunity, and now I'm looking at what's inside the brackets, which is actually just division again. We have d being divided by 8. How do we get rid of that? Well, multiply by 8. If I do it to the right, I do it to the left. We end up with 88 equals d, or d equals 88. So the depth that you are at with a water temperature of 5.5 degrees Celsius is 88 meters. And since we're at the bottom of the lake, we can say the depth of the lake is 88 meters. Are there different ways we could have done this algebra? Yeah, for sure. Okay, we could have not done each calculation on the left side and just saved it for the end and done it all in one calculation. Another thing that that I will almost always do is, instead of writing this step as 11 over equals d over 8, I'll right away just swap them so that my variable is on the left, and I have d over 8 equals 11, which is the same, and then go from there. It's easier to work with your variable being on the left side right away. It makes no difference. A equals B is the same as B equals A. All right, my friends, that's it for lesson 1.2. Your practice problems come from page 22, 1 through 3, 5 through 7, and 10. Page 22, numbers 1 through 3, 5 through 7, and 10. Go for it.